In the last class, we learned how to apply the chi-square technique of hypothesis testing, and we saw an example in the last class. Today, let us continue with that with another example. It is normally believed that those who have a high IQ measured at a relatively young age will have a larger promise of intellectual success at a later age. And suppose you are testing out, you are setting out to test that belief. How do you do that? This is how it is conducted. Suppose that first you get a collection of 15-year-old kids from a school, more or less of the same academic background as well as financial background, so that their financial status, social status is more or less the same. And suppose you have got some 100 kids like that, and you test their IQ and divide them into 3 categories: IQ less than 80, IQ between 80 and 100, and IQ greater than 100. And then you wait for 15 years, and after 15 years you check the intellectual success of each one of these 100 kids and divide them into 2 categories depending on the answer to the question: did they excel in any intellectual pursuit or did they not, yes or no. Accordingly you divide. So, the result suppose you got is something like this, that initially when you made the test, 16 kids were in the IQ less than 80 category, and out of that 4 have excelled in intellectual pursuit, 12 have not. In the middle one, that means from 80 to 100 IQ, there were 66 kids, out of whom 19 excelled in intellectual pursuit, some kind of intellectual pursuit, and 47 did not. And 18 kids had IQ greater than 100, and out of that 9 excelled and 9 did not. So, on that basis, can you infer that IQ is an indicator of promise of intellectual success? This is the problem that we are tackling now, suppose. Now, you notice that out of 100 kids, 32 excelled in intellectual promise. So, overall probability of intellectual success is 32 by 100 is equal to 0.32. Now, in this case, what is the null hypothesis and what is the alternative hypothesis? The null hypothesis H naught is the probability of intellectual success is independent of the measured IQ. Of the measured IQ. And what is the alternative hypothesis? That says the same, dependent. So, this is dependent. Now, we have said that whenever we set out to test a hypothesis, we always root ourselves on the null hypothesis and check if there is enough evidence to reject the null hypothesis. So, if the null hypothesis is true, then our expectation would be that in all these categories, there would be the same ratio of intellectually successful people. So, this ratio will remain the same irrespective of whether one is in this category or this category. which means from there we can draw the expectations. So, let me write expectations, expected number. So, out of 16, 0.32 will be 0.32 times 16 should be expected to find intellectual success, that comes to be 5.12. 16 times 0.32 will be 10.88. That is basically 16 minus 5.12 is 10.88. So, remaining number should not be expected to be intellectually successful, and these two also adds up to 16. Similarly, here the intellectual success, the probability of intellectual success of all 66 people should be the same if the null hypothesis is true. So, 66 times 0.32 is 21.12, and 66 minus 21.12, that many number will not be expected to be successful. That number is 44.88, 44.88, and this is totally also 66. This total is out of 66. Similarly, this is expected. Here also there will be an expected. That number will be 18 times 0.32. That number will be 5.76, 5.76, and this is again 18 minus 5.76, it would be 12.24. And you notice that all these rows add up to these numbers, all these rows add up to these numbers, and all these columns also add up to this number. So, 4 plus 19 plus 9 is equal to 32, 12 plus 47 plus 9 is equal to 68, and so on and so forth. So, this is the contingency table for this particular problem. Okay. Now, we set out to do the chi-square test. Now, how would you do the chi-square test? We have to write the value of chi-square. So, let me put it like this here. So, we have to write the chi-square, and chi-square, as you know, is a sum of the expected minus the observed square divided by the expected. So, the first row will be 4 minus 5.12 whole square divided by 5.12 plus it will be 12 minus 10.88 square by 10.88 plus now the second row 19 by 19 minus 21.12 square by 21.12 plus 47 minus 44.88 square by 44.88 plus 9 minus 5.36 by 5.36, this one will be square, plus 9 minus 12.24 square by 12.24, and this calculates to 3.353. Okay. So, now this is the chi-square value for this particular contingency table, and if this is the chi-square value, then we will consult the chi-square table to find out. Okay. Before we do that, we need to find out the degree of freedom. So, what is the degree of freedom in this case. The degree of freedom, here there are three rows, but then if you know the total number, by knowing two of them you can calculate the third. So, the third one does not have a degree of freedom. So, vertically around the rows there are 2 degrees of freedom. Along the columns there are 2 columns, but if you know the total, you can, if you know one, you know the other. Therefore, along the vertical you have only 1 degree of freedom, and we said that it is basically n minus 1 times m minus 1. In this case it is 3 minus 1 times 2 minus 1 is equal to 2. So, it is only 2 degrees of freedom. So, now with that information we consult the chi-square table. I have already shown you in the last class how to consult the chi-square table, and you consult the chi-square table and find that in order to reject the null hypothesis, you need a chi-square in order to reject the null hypothesis with 95% confidence. So, to reject the null hypothesis, I would say required chi-square. Required chi-square will be 5.991 with confidence level 95%. That means significance level 0.05. You notice that this is below that, this value is below that, and if the confidence level is even lower to 90%, then it would be 4.605 with confidence level 90%. So, it is even below that, which means that the differences, even though to an untrained eye it looks like among the number that is below 80 IQ, a larger fraction did not perform intellectually, but these variations then appear to be satisfying the requirements of a random distribution, because we cannot reject the null hypothesis even with 90% confidence. We cannot with 95% confidence, we cannot even with 90% confidence, we cannot reject the null hypothesis. And so, on the basis of this data, we would say that we do not have enough evidence to reject the null hypothesis. And on that basis, we will accept the null hypothesis that there are factors other than IQ that are principally responsible for one's intellectual success in life. The way is an individual conducts a life, how he learns from the surroundings even after the age of 50. So, these are many cases the more important determining factors in deciding the intellectual success in one's life. Now, so far we were dealing with the chi-square tests where we were putting individuals in categories. The tall plants, the short plants are the categories. Somebody in a IQ level between below 80 is a bin, a category in which you can put an individual. So, in that kind of situations we have learned how to do the test. But there are also situations, especially in natural sciences, where a hypothesis or a theory predicts a value, not whether how many can be put in a bin, but rather a value. And how do you test that kind of a hypothesis or a theory in that situation where it is a value that is predicted. Okay. So, firstly our logic was that we will subtract the expected value, we will perform the test experiment, and then there would be some, in that particular experimental condition, there should be some expectation from the theory, and the expected value and the observed value, the subtraction of that, it does not matter whether you subtract this from that or that from this, because ultimately you take a square, so that it becomes a positive number. So, we are essentially dealing with, so here we are talking about chi-square test for comparing measurements. With some expected value. So, there is some expected value, and if you are, if an experiment has an expected value E and the observed value O, then we are talking about the observed value minus expected value square. Now, we have learned that this needs to be normalized. In this case, what will you normalize it with? Now, the difference between the observed value and the expected value could be due to some kind of a systematic factor, for example, the theory being wrong, or it could be due to random errors, and therefore, it is logical to compare that with the typical error level of that particular experiment. So, the typical error level is say the error level, sorry, in that experiment is say delta the observation. Okay. Now, what is that? We have learnt earlier that if you make a measurement a number of times and take the mean, then from there you can find out the standard deviation, and the standard deviation divided by square root n is the standard error of the mean, and the standard error of the mean is a typical indicator of the error level of the experiment. So, this is essentially the standard error of the mean. We know how to do that. So, we will have to normalize it by the standard error, right, delta O. But this, in the case of where we are making measurements, these could have units, for example, centimeters or grams per second or whatever. So, you have these are units, but the chi-square should have no units, it should be non-dimensional, and therefore, you have to divide it by delta O square. So, that would be the chi-square. Now, this is true if you are able to make one measurement, but a theory may predict different outcomes for different conditions in a measurement, and therefore, we have to make provisions for a number of such measurements being done, and for each one there is an expected value. And if we keep that provision, it would have a subscript I, the ith measurement, and the ith prediction, and the ith, and then you have to sum over all i's. Okay. Suppose there are a theory predicts m number of different situations in which for each situation there is a expected value, you measure it, you get the corresponding observed value, and you also get the corresponding standard error of the mean, and then this will represent in that case the chi-square value, and the rest of the test is the same. Remember that in that case the standard error has to be measured in a proper way as we have learnt earlier, which means you have to take 25 readings, you have to otherwise it will not be distributed as a normal distribution. The normal distribution has to be guaranteed in order for this to work, and then you extract the standard error of the mean, which is basically the sigma by square root of n, and if you do not know the sigma, then it is the measured standard deviation divided by square root of n. Okay. So, this will have to be substituted here. Okay. Now, let us illustrate this method using an example.